Hello students, welcome back to A-Star Tuition channel. Today we'll continue our discussion about dynamics. Specifically, we'll discuss about work, power, and energy. Let's start. We'll begin our discussion with the definition of work. So what is work? So in physics, if you have a force acting on an object and that the object is displacing or experience displacement, then we say that this force is exerting work to the object. In fact, the definition of the work done by a force is equal to the product of displacement of the object with the parallel component of the force. Let's write it down as the component of the force parallel to the displacement. Okay? Let me illustrate here. So let's say that this is a block that you put on top of a table and that there is a force acting. This is a pulling force and this force is inclined at an angle of theta with respect to horizontal, and that the object is displacing or is moved by S. Yeah. So the question is, what is the work done by this object? Okay, now in this case, the work done, based on the definition, you multiply the displacement with the component of the force parallel to the displacement. Now you see that this force here is directed at angle theta with respect to horizontal, but S is horizontal, so therefore what you need to do is you need to resolve F in the direction that is parallel to the displacement, and this is F cos theta. So the work done is W equal to S times F cos theta, or we can just write it as F times S cos theta. Now in a lot of situation where the force itself is already parallel to the displacement, then the theta is 0. So in that case, when theta equal to 0 degree, in other words, the force is parallel to displacement, then the work done is simply the product of F and S. Now on the other hand, when the angle is 90 degree, then in this case the force is perpendicular to the displacement, and that in that case the work done by this force is equal to 0. Cos 90 degree equal to 0. Now in the previous case we assume that the force is constant. However, when the force itself is changing as the position changes, then we can actually obtain a graph of force versus displacement. Yeah, like this force displacement. This is example. Yeah. So in this case, the area under the graph represents the work done, yeah, from position A to B. So when the force itself is not constant, well, when the force is constant, you can also use this, this method. But the previous method only works when the force is constant. Now, when the force is not constant, aka the force is changing with respect to the position, then you can find the work done equal to the area under the force versus displacement graph, yeah, from point of interest. Like for instance, here I'm using A and B. this tells you that, oh, the area under the graph between A and B represents the work done by this force in displacing the object from position A to position B. Now, please understand that sometimes when the graph is below the x-axis, then that means that the work done is negative. Now in this case, you can see that all of them is above the displacement axis. But then if some of the graph is below that, then the area itself is still positive, but the work done must be assigned negative value for those values that is below the x-axis. Now, I also want to mention about the unit used for work done. Now, remember, this is how you define the work done. Yeah, so this is equal to force S cos theta. Now, cos theta itself has no unit, but force has a unit of Newton. Remember, Newton or kilogram meter minus 2. This is in second. So Newton times second, and this is actually kilogram meter second minus 2, yeah, and then this is second. If you multiply with this, you end up with kilogram meter minus 2 meter. Actually, this is not in second, this is meter. Kilogram meter second minus 2 times meter, so it's going to give you kilogram meter square second minus 2. So this is the fundamental unit for work. Yeah. Now there is actually an abbreviation for this, and this abbreviation is called joule. Yeah, joule. Now joule is obviously named after a scientist, yeah, or an engineer who I think discovered something related to how to make use of the work. Yeah, so joule is the SI unit for work, either kilogram meter square second minus 2 or joule. Don't forget that. Next, let's talk about the notion of energy. Now, what is energy? Energy is the entity that is possessed by something or someone in order to perform work. For instance, every one of us has what we call as energy. We need energy to walk, to run, or even to stand. We require energy, and we obtain that energy from the food that we consume. Now, object can also have energy. Like for instance, let's take a look at a catapult, for instance. Now, when you try to stretch the catapult, it has some energy stored within it. Now, when you release the catapult, it has the ability to perform work, which is to throw or to catapult the small rock that you put in the catapult to begin with. Now, when we talk about mechanics, there are actually two types of energy to discuss, which is kinetic and potential. Now, what is kinetic energy? Kinetic energy is actually the energy that belongs to an object when the object is moving. In fact, if the object has a mass of m with speed v, then the kinetic energy Ek is equal to 1/2 times mass times the square of the speed. And again, if you look at the unit, this is in kilogram, this is meter per second square, so it becomes kilogram meter square second minus 2. So this is exactly the same as the unit for work. So this is also equivalent to that, which is joule. Now, potential energy is different. Potential energy of an object is due to the fact that the object itself is interacting with other object. Okay, now there are actually many examples, but let's discuss about the gravitational potential energy. Gravitational potential energy. Let's call it GPE. So any object that is located on Earth, it doesn't have to be Earth, but like a large enough body of mass in which everything is bounded to, like a planet, for instance. But then, well, Earth itself is one example of a planet. So GPE of an object that is bounded to the planet, as long as it's located relatively close to the surface of the planet, in other words, the distance is less than 1 kilometer from the distance of the planet, the G is constant, so therefore we define that as mgh. Now, please understand that unlike kinetic energy, gravitational potential energy is not an absolute quantity. It's a quantity that is relative to a reference point. Now, the reference point that we usually use is the ground. So, for instance, the GPE would be different if you define if you define the 0 point or the reference point as, let's say, the ground or maybe the surface of a table. So then this is an object. Let's say that this is like 2 meters above the table, and the table itself is, let's say, 3 meter height. Now in this case, the gravitational potential energy of the object would be different if you calculate from the surface of the table or from the ground. It would be different, so it's relative. But at the end of the day, it actually doesn't matter which you choose as the reference, because in calculation, we only need to calculate the difference. So then, when choosing a reference point, you can just use the ground in general, but you can choose any point as the reference for your convenience. Just make sure that you are consistent with that reference point. Okay, next, let's talk about power. The notion of power is actually, it's about rate of change of energy, or rate of change of work done. So how you define power, you can actually define as the rate of change of work performed. Or you can also alternatively write it as the rate of energy usage. So how fast is energy is used. So, example, if you try to, let's say, lift a very heavy object. Now when you lift a heavy object, let's say, from the ground until like 1 meter height, or maybe 2 meter height from the ground. The thing is that when you do that, you need to use that energy very fast, relatively fast. So you have to make use all of the energy that you have at small amount of time. However, when you sit down, or maybe when you stand like this for quite some time, then the energy required is also the same as the energy required to lift that heavy object. So the only difference here is the time. So it will take longer time for somebody to stand until the person expend or use the same amount of energy as the person would if the person is to lift that heavy object from the ground until, let's say, 1 meter above the ground or 2 meters above the ground. So please understand that the difference between work and energy, power and energy. Another example would be like someone will use the same amount of energy to walk 1 kilometer as he would if he is to run 1 kilometer. So the energy required is the same. It's just that the power will be greater for those who is running, because the person need to expend the energy at smaller amount of time. So based on that, power can be written as work per unit time or energy per unit time. Now remember, work and energy, they both have the same unit, which is joule, and this is second. So this is joule per second, and joule per second is denoted as W, aka watt. Now again, this is like the last name of a scientist who discovered something. Yeah, so I think it's about steam engine, something like that. Yeah. So, but then remember, don't forget that joule itself is kilogram, meter square, second minus 2. So then watt is actually equivalent to kilogram, meter square, S minus 3. Yeah, so this is the unit for power. Okay, now one of the example how you can also calculate power is this. Yeah, so this is work, this is time. So the work, remember, is equal to F times S. If we imagine that the cos theta is equal to 90, cos theta is 1, aka is 90 degree, 0 degree, then this become F times S over T. Now S over T is the speed, yeah? So it's the rate of change of displacement, which is speed. So then alternative way to calculate power is to multiply the force to perform the work multiplied by the speed. So then you can see that it depends on the speed at the time. So the greater the speed, the greater the power from this relationship. Last, let's talk about the notion of efficiency. So when you perform a work, now not all of the work is actually useful, because some of the work that you perform is probably lost as something else, yeah, like heat or sound. So there's energy that is lost when work is performed. So efficiency of work performed is defined as the energy, the output energy, output or useful energy, divided by the input energy, the input or supplied energy. In other words, you supply an energy to perform work, but only this energy that is obtained. Or like for instance, when you increase, let's say that when you want an object, that you raise the object by a height, by a certain height, let's say h, right? H is 1 meter. Let's say that the mass is equal to 1 kg. So then you can see that the potential energy increase is equal to 1 times 10, G is 10, yeah, 10 joule. However, the energy that you supply to increase the potential by 10 joule is probably greater than 10, maybe 15, 20. Now in the case of 20, then 10 is the useful output energy over the supplied energy, and then you multiply by 100%. So this is going to give you 50%. So the efficiency actually has this symbol, yeah, Greek symbol. So the efficiency of the work performed is 50%. Okay. Now this quantity, because of the way you define it, has no unit, yeah. But efficiency doesn't need to be performed in doesn't need to be defined in terms of work, but it can also be defined in terms of power. So you can write it as output power over input power. So it doesn't have to be in terms of energy. Yeah. So either you use output power per input power, or useful energy over supplied energy. Now as long as you're consistent, yeah, don't use output power over input energy. So because it's not the correct comparison. So you have to use the power versus power, either output power versus input power, or output energy versus input energy. Yeah. So this is how you define efficiency, and efficiency basically tells you how much of the energy or the power that is given to a system that will actually be used for the performance of the system. Okay, so that's it for the lesson today for dynamic. I hope you learned a lot from this video, and we will actually continue our discussion for dynamics in the next video. Don't forget to like, subscribe, and share the video. I'll see you next lesson.